In this lecture, we're going to prove one problem, satisfiability for Boolean expressions, to be NP-complete by showing how to reduce the language of any non-deterministic polytime Turing machine to satisfiability. We will then cover two of its restricted versions called CSAT and 3SAT respectively. We'll learn shortly what those mean. Our first step is to learn about Boolean expressions, or what is the same, expressions of propositional logic. These expressions consist of constants, variables, and the operators and, or, and not. There are only two constants, true and false, which we'll usually represent by 1 equals true and 0 equals false. The variables can only take on these two values as well. The operators and, or, and not have the usual logical meaning. When we write these expressions, we'll use concatenation, that is, no operator symbol for and. So xy really means x and y. We'll use plus for or, so x plus y means x or y. And we'll use the minus sign for not, so minus x really means not x. Here is an example of a Boolean expression. X or y is true when at least one of x and y is true, and not x or not y is true when at least one of x and y is false. So the whole expression is true when at least one is true and at least one is false. Since there are only two variables, that means exactly one is true and exactly one is false. As for any kind of expression, remember to use parentheses to alter the order in which operators are applied. The order of precedence is not first or highest, then and then or. Thus, the parentheses in the example expression are needed to make sure that the ors are applied before the ands. A truth assignment is an assignment of 0 or 1, that is false or true, to each of the variables of a Boolean expression. In general, the key question about Boolean expressions is which truth assignments give them the value true. But for our NP-complete problem, we need only this very simple question: given a Boolean expression, does there exist at least one truth assignment for which the value of the expression is true? So this expression is satisfiable. There are, in fact, two satisfying assignments, those that make one of x and y true and the other false. But this expression, x and not x, is not satisfiable. There are only two truth assignments. X can be assigned true or it can be assigned false. If x is true, then not x is false. That is the and of expressions, one of which is true and the other is false, has value false. Similarly, if we assign x false, then x is false while not x is true, and the and of these is again false. We must see the SAT problem as a language, just like all the other problems we've discussed. First, the instances of the SAT problem are all the Boolean expressions. Since expressions can have any number of variables, we must code expressions in a finite alphabet. The parentheses, the plus and minus, can represent themselves, but we need to have a scheme for representing variables. We'll represent the ith variable by the symbol x followed by I in binary. So here is an example of an expression coded this way. We've assumed that x is the first variable, so it is represented by an x followed by 1. That appears here and also there. Y is the second variable, so it is represented by x and 2 in binary, that's x, 1, 0. What we call the variables doesn't matter as far as satisfiability is concerned, so we could have called y the first and x the second. Generally, the easier part of proving a problem NP-complete is proving it is an NP. Generally, you just guess a solution and then in polynomial time you check it. And the SAT problem is no exception. Okay. Well, we need to describe a non-deterministic Turing machine that can take a coded Boolean expression as input and tell if it is satisfiable. And of course, the non-deterministic machine must be polynomial time-bounded. In this case, order n squared time suffices. The power of non-determinism lets us guess a truth assignment. We'll use a second tape to write down the guess of a truth value for each variable. Then, in the expression itself, replace each variable by its guessed truth value. We can now evaluate the expression bottom up. The non-deterministic machine accepts if the value of the expression with this assignment is true. Notice the power of non-determinism here. The number of assignments could be exponential in n, the length of the expression, but the non-deterministic machine works on all the expressions sort of in parallel, thus appearing to finish in time that is polynomial in the input size, because we only count the time taken for processing one single assignment. Also, notice that non-determinism is more than parallelism. Given any fixed number of processors, say 1,000, we could divide the time needed to evaluate the effect of each truth assignment into 1,000 groups and evaluate them in parallel. But if there are 2 to the n assignments, it would still take each processor time 2 to the n divided by 1,000, which is still exponential in n. We're now going to give the proof of Cook's theorem that the SAT problem is NP-complete. Since we don't have any NP-complete problems yet, we can't do a reduction from some one other problem to SAT. Rather, we have to show how to reduce any problem in NP to SAT in polynomial time. We do these reductions by assuming nothing about the problem L that is in NP, except that it has some non-deterministic polynomial time-bounded Turing machine that accepts L. To make the reduction from these Turing machines to SAT easier, we're going to make some restrictions on the Turing machine, but only restrictions we can assume without losing any of the problems in NP. That is, every problem in NP has one of these machines, which we'll describe on the next slide. The restrictions we make are the following. First, that the non-deterministic machine has only one tape, and that the head never moves left of its initial position. We'll assume the states are never also tape symbols, so we can tell which symbol in an ID is the state. Point 3 clearly loses us nothing, since we can always change the names of the states without changing what the machine does. And we've already seen the constructions many tapes to one and two-way infinite tape to one-way. Each of these constructions can square the number of steps the Turing machine makes, but that's okay. The square of a polynomial is still a polynomial. This slide has a collection of random but important comments about what we assume about the non-deterministic polytime Turing machine M, in addition to the restrictions we assumed on the previous slide. First, let P of n be the particular polynomial upper bound on the running time of M. We'll be simulating M on an input W, which is of length of n. This next assumption is really about how we define the next ID relation. We're going to assume that if M accepts W, then there is a sequence of exactly P of n moves from the initial ID with a final state in the last ID, and perhaps other IDs as well. We're going to assume that if M is in an accepting state, then the identical ID represents one legal move. So if M enters an accepting state early on, then the sequence of IDs leading to acceptance can be extended to length P of n by repeating the first ID that has an accepting state. There is no harm in doing this. M is already accepted, so entering an accepting state more than once will not change anything. And this is an observation rather than an assumption. Remember that the head cannot move more than P of n squares in P of n moves. So we're going to represent each ID by a sequence of exactly P of n plus 1 positions, the first P of n tape squares, and the state. Initially, most of these are blank, but it's okay for some of these P of n plus 1 positions to hold a blank beyond where the head has reached so far, even if this blank is not technically part of the ID. We have to design a polytime transducer that can turn the input W into a Boolean expression that is satisfiable if and only if M accepts W. The transducer is designed knowing M but not W. The first thing the transducer does, seeing W, is to determine its length n. The expression that is output from the transducer will involve P of n plus 1 all squared, what we call variables. But these variables are not the propositional variables of Boolean logic. Rather, they are collections of propositional variables that together represent the symbol in a particular position of a particular ID. That is, the variable we'll call xij represents the jth position of the ith ID. Thus, I and j are each in the range 0 through p of n inclusive. Think of the variables arranged in an array. The rows represent successive IDs, and the columns represent positions in those IDs. We'll start with the initial ID, with the start state, input w, and the rest of the positions blank. We'll design the expression to be satisfiable if and only if m accepts w. We'll see that the expression constrains the values of the variables so that the only way the expression can be satisfiable is if each ID represents a move from the previous ID, or the previous ID has an accepting state and the next ID is the same. And the expression also requires that the state in the final ID, I sub pn, is an accepting state. Thus, from m, which it knows, and w, which it sees, the transducer constructs an expression. Any satisfying truth assignment for this expression will give the x's the proper values that form an ID sequence of m with input w, leading to acceptance. Now remember, the x's are not Boolean variables. They represent states and tape symbols of m. However, each variable can take on only a fixed number of values, the sum of the number of tape symbols and the states of the known Turing machine M. Thus, we can represent each xij by this number of propositional variables, exactly one of which can be true. That is, for each state or tape symbol A, let y sub ija, that's this, be a propositional variable, and we want y sub ija to be true if and only if x sub ij equals a. As we describe the construction of the Boolean expression, we must make sure that we take time that is only a polynomial in n. There are many components from which the final expression is built, but they fall into two classes. Some depend on w and therefore depend on n. These components are and must be of size that is a polynomial in n. And more importantly, we can write them easily so that the time taken to write them on the output is polynomial in n. The second kind is those that depend only on m. These take a constant time as far as input size is concerned. That is, m may have lots and lots of states and lots of tape symbols, but these quantities are independent of n, so as far as we're concerned, they're all just constants. And to make our lives a bit simpler, don't forget that if an expression has a set of arguments whose size is fixed independent of n, then no matter how large the number is, it is a constant as far as n is concerned. So the time to write any such component is a polynomial in n. In fact, it's a 0th degree polynomial. Now let's start to describe the output of the transducer. The output is an expression, and we want it to be satisfiable if and only if m accepts w. The whole expression is the AND of 4 sub-expressions, each of which enforces one of 4 conditions. First is the sub-expression we'll call unique. It enforces the rule that there is only one symbol in each position of each ID. That is, the value of xij is unique. The second sub-expression is starts right. It forces the initial ID to be the start state followed by w. The next is moves right. This really should be moves correctly, but that's too many syllables. This expression enforces the condition that each ID follows the previous ID by one move of m. And as that convenient exception, if the previous ID has an accepting state, then the next ID may be the previous ID. Finally comes the expression finishes right. This condition says that somewhere in all that stuff is an accepting state. For unique, we use the AND over all IDs I, positions j, and states or tape symbols y and z of the expression, not y sub ij capital Y, or not yij capital Z. This little expression is satisfied as long as at most one of the two Boolean variables, yij cap y and yij cap z, is true. Put another way, if xij were to have two different symbols, say cap y and cap z, then one of these little expressions would be false. But unique is the and of all these expressions, and the entire expression is the and of unique and the other expressions. Thus, the entire expression cannot be satisfied by any truth assignment that makes any pair of variables yij and yijz both be true. Now let's formulate starts right. This expression requires the first ID to be the one m starts in with input w. Let w, whose length is n, consist of symbols a1 through an. We want x00, the first position of the first ID, to be the symbol that is the start state of m. That's used conventionally q0. And we want the next n variables to represent w. That is, x0i must be ai for all I up to n. And all the other positions of the first ID are blank. That is, x0i is blank for I between n plus 1 and p of n. But there's a propositional variable for that. Each of the conditions that makes up starts right is of the form some one of the x variables is a particular symbol. But that's what the propositional variables yija do. So we can write starts right as the and of y sub 0, 0, q0 and y 0, 1, a1, the first symbol of w, and y 0, 2, a2, and so on, and after, let's say, y0 n an, then you got to have y0 n plus 1 comma blank, and so on. So finish is right is easy. M accepts if and only if the last ID has an accepting state, because once M enters an accepting state, it appears to stay in that state until the ID numbered P of n. So take the OR of the Boolean variables y sub P of n, j, and q, where q is an accepting state and j is anything from 0 through P of n. Now let's see how long it takes to write down the three of the four expressions we have described. Remember, we have yet to describe the hard one, moves right. Unique is actually the most time consuming. It requires that we write down big O of p squared of n symbols. The p squared comes from the fact that we range over all I and j between 0 and P of n. The constant factor comes from the fact that for each I and j there are a large but finite number of pairs of states and or tape symbols, each of which needs a little expression. The number of pairs may be large, but it is independent of n, so it is a constant. And that expression involves two parentheses, three logical operators, and two propositional variables, only a constant number of things. But let me remind you again that the real issue is not how long the expression is, but how long it takes to write it. But the expression is simple, and it is simple to write the expression by looping on I and j, thus taking time proportional to its length. Starts right is the and of P of n propositional variables, and again the pattern is simple, so we can write this expression in order P of n time. The same holds for finishes right. There are P of n propositional variables, and we need to output those variables connected by ORs. Oops, I lied. The running times are a little larger than I said. Not enough larger to take us out of the polynomial class, but larger by a factor of log n. That is, I cannot really output a propositional variable like y sub ija in one step, or even a constant time. The reason is that we have to use a finite alphabet to represent order p squared of n propositional variables. We agreed to represent a variable by the symbol x followed by an integer in binary, like this. To represent order p squared of n variables requires integers whose length is order log n. But this is no big deal. A factor of order log n is less than a factor of n, so all it can do is raise the degree of a polynomial by 1, not even that much. So in what follows, we're going to ignore factors of log n and just assume we can write down a propositional variable in constant time and space. We're now going to start working on moves right. A lot of this expression simply says that xij equals xi minus 1j. That is, a symbol in the ith ID is the same as the symbol in the same position of the previous ID. That will be true whenever the symbol in that position is not the state, and neither are the positions to the left and right in the previous ID the state. Since a state can only move one position, we know nothing changes two or more symbols away from the state. So we're going to construct one sub-expression for each I and j saying that either xij equals xi minus 1j, or the state is lurking about. The idea that the state is lurking is the or of those propositional variables y sub I minus 1 k a, where k is within 1 of I and a is a state symbol of M. Now we need to translate the equality of xij and xi minus 1j into propositional variables, but we just need the or of yija and yi minus 1ja, that's this, for all symbols a. The reason that works is that we already have unique to enforce the condition that for only one symbol a can yija or yi minus 1ja be true. The expressions we constructed for each ID I and position j will be part of moves right. Each says colloquially that the tape symbol can't change if the state isn't nearby. They will be ANDed together with expressions that enforce the correctness of the moves of M for the case when the state is nearby. To write the expression for moves right, we need to consider both the case on the left, where a position holds a tape symbol, and so do its neighbors to the left and right, and the hard case on the right, where the state is nearby. In the easy case, there is no doubt that the symbol in position j of the ith ID is the same as the jth symbol of the I minus first ID. We already covered this case in the previous slide with the expressions that say if the state is not nearby, then the symbol doesn't change. But in the hard case, there are three positions, the positions that hold the state in the I minus first ID and its neighbors, that can be affected by the move. Moreover, since we're simulating a non-deterministic Turing machine, there may be a choice of move, and we need to coordinate the three positions in the ith ID to make sure that all three reflect the changes of a single choice of move. For the hard case, the pieces of the moves right expression must do two things. It has to pick one of the possible moves of M, that is, a state of Q, a tape symbol A, and a direction, that is, the choice of one of the triples in delta of Q and A. And then, for that move, it must enforce the condition that when the jth position of the ID I minus 1 holds the state Q, and the j plus first position of the I minus first ID holds a symbol A, then in the ith ID, the positions j minus 1 through j plus 1 reflect that move. Note that either the j minus first or the j plus first position is unchanged, so the expression also has to enforce the condition that this position is unchanged from the previous ID. That is, suppose delta of QA contains, perhaps with other choices, a leftward move going to state P and writing B over the A. That would be that. Then, for any IDI position J and tape symbol C, that is, this is ID I minus 1, that's I. This is position j minus 1, that's j, and that's j plus 1. Okay. Then, one possibility for the 6 variables represented by this rectangle, that is this, is the combination that is reflected here. That is, P has moved, the state has become P has moved to the left. The C is unchanged, but its actual position is different, and the A has been replaced by a B. Similarly, if the move is to the right, that is something like that, then the 6 values are the ones we must enforce for the variables in this rectangle. And those, well, the C doesn't change at all. The state Q becomes P and it moves to the right. So it's here, and then the A got replaced by B, and the B appears over here. Now we can assemble the parts of moves right that enforce the moves. We already gave the formulas that say if the state is none of x I minus 1 j minus 1 through x I minus 1 j plus 1, then xij equals x I minus 1j. That is, you can't change a symbol if the state is not nearby. Now we have to include expressions that constrain the 6 variable x's that are near the state in the I minus first ID. For each possible move, write an expression for each position j and each ID I that expresses the constraints on the 6 relevant x's for that move. There is one more type of move of m that isn't really a move. We need to allow no change in ID if m is an accepting state. For each accepting state of m, there's a fake move in which nothing changes. For each I and j, take the or over all moves of m of the expression you just wrote for I and j. Now, for each I and j, you have an expression that says the 6 relevant x's reflect some move of m. Take the and of these expressions over all I and j. Also include in the and all the expressions from earlier that say symbols don't change if the state is not near. Okay, there's a small glitch in all this material. We assumed position j was not 0 or p of n, the leftmost and rightmost positions that are represented by the IDs. If j is one of these, there are only 4 x's involved, and we need to modify so that the missing symbols are assumed blank. The same fix-up is needed for the rules that say the symbol doesn't change if the state is not nearby. If the symbol in question is at one of the n positions 0 or n, then there is no possibility that the state is outside this range, and we can omit that requirement. Now consider how long it takes to write down the moves right expression. Moves right consists of the and of 2 p squared of n expressions, 2 for each ID I and position j. One of the 2 is the expression that says the symbol doesn't change if the head is not nearby. The other says that if the head is nearby, then the 6 relevant symbols are related in such a way that they reflect one move of m. Each of these expressions can depend on the number of states, symbols, and moves of m, but none of this depends on n. That is, as far as the length of the input w is concerned, each expression is of constant size. We claim that each of the order p squared of n expressions is easy to write down in time proportional to their length by a transducer that knows the moves of m. So the transducer can output moves right in time that is polynomial in the length of its input w. As always, there is another factor log n because we must write the Boolean expression in a fixed alphabet, but factors of log n cannot take us out of the polynomial class. So, to sum up the proof of Cook's theorem, it takes time less than order p cubed of n for the transducer to output the Boolean expression that is the and of the 4 key components: unique, starts right, finishes right, and moves right. We claim that this transduction really is a polytime reduction of the language of m to the language sat. First, if m accepts w, then there is some ID sequence that leads to acceptance. Imagine the p of n plus 1 by p of n plus 1 matrix of the xij's. The accepting sequence of IDs lets us fill out this table correctly, giving the value to xij that reflects the sequence. The expression we constructed will be satisfied when we assign to the propositional variables yija the truth values implied by this choice of xij's. So if m accepts w, then the expression is satisfiable. Conversely, if we have a satisfying assignment for the expressions, we can get unique values for the xij's from the propositional variables. The unique expression assures that the xij's can be given unique values. And starts, finishes, and move right assure us that the xij's form an accepting computation of m with input w. That is enough to show that every polytime non-deterministic Turing machine's language is polytime reducible to sat. We now have one problem, sat, that we know to be NP-complete. We're going to reduce it to other problems in order to show them NP-complete as well. but it is easier to polytime reduce a special case of SAT called 3-SAT to other problems. So our first step is to show that SAT is NP-complete even if the Boolean expression is in a very special form. The first restriction that we place on expressions is that they be in CNF, that is, conjunctive normal form. These expressions are the and of clauses, and a clause is the or of literals. And a literal is either a propositional variable or its negation. So our next step will be to show to be NP-complete the problem CSAT, which is whether a Boolean expression in conjunctive normal form is satisfiable. Here's an example of a CNF expression. The first clause, it's this, is x or not y or z. That is, x, not y, and z are each literals. The second clause is just this, not x. That's okay. A clause can be the or of only one literal. The third is the or of four literals, which are not w, not x, y, and z. Okay, we're not going to reduce SAT to CSAT. Rather, we'll examine Cook's proof and see where it needed to be fixed up to make the output expression be in conjunctive normal form. That way, we will have a direct reduction of every problem in NP to CSAT. Okay. Everything but moves right is already in CNF. You can review the constructions, but when you do, you'll find that unique is the and of clauses. So is starts right. In fact, each clause has only one literal, which is in fact an unnegated variable. And finishes right is the or of unnegated variables, and therefore is a single clause. Now let's look at moves right. It is the and of an expression for each I and j, where I is an ID number and j a position in that ID. Recall this expression says that either the head is not near position j, and the symbol in position j of ID I is the same as the symbol in the same position of the previous ID, or the head is at position j in the ID I-1, and three symbols of ID I around position j reflect one move of the polytime Turing machine M. Here's the subtle thing. As complicated as these expressions are, they depend only on M and not on the input length n. As a result, we can write the expression for a given I and j in conjunctive normal form. It is possible to convert any Boolean expression to conjunctive normal form. I'll show you the trick on the next slide. This conversion does, in the worst case, exponentiate the length of the expression, but it doesn't matter in this application because the only expressions to which we need to apply the conversion are expressions whose size is independent of the input length n. Thus, the time taken to convert to CNF for each expression is just some constant, independent of n. Here's how we'll convert a given Boolean expression to CNF. We'll consider each truth assignment that makes the expression false. Note that if there are k variables in the given expression, there could be 2 to the k such truth assignments, and the resulting expression will take that much time to write down. But again, we're only exponentiating a constant, and the result is still independent of the input size n. For each such truth assignment, we construct one clause. If variable x is assigned true in this truth assignment, then the clause has literal not x, and if x is assigned false, then the clause has literal x. That way, the only time the clause, which is the or of all of these literals, is false, is if this is the exact truth assignment. The resulting CNF expression is the and of the clauses for each truth assignment that makes the original expression false. Thus, the CNF expression is made false exactly for those truth assignments that make the original expression false, and therefore it is, of course, true exactly when the original is true. For example, consider the expression not x or y and z. This expression is made false by 3 truth assignments, those in which x is true and at least one of y and z is false. Let's convert the first truth assignment, where x and y are true and z is false. Here is the resulting clause. Since x and y are assigned true, the clause has not x and not y. Since z is assigned false, the clause has z without negation. Notice that the only way to make this clause false is to make each literal false, which means giving each variable its value from the truth assignment that generated the clause. The other two truth assignments generate the next two clauses, this and this, and the entire CNF expression is the AND of the three clauses. It is therefore made false exactly when the variables are given one of the three truth assignments. A Boolean expression is said to be in K-conjunctive normal form, or KCNF, if it is the AND of clauses, each of which contains exactly K literals. The problem KSAT is whether a KCNF expression is satisfiable. For example, the expression we derived on the previous slide, which we show here, is in 3CNF. Notice it is the AND of clauses, and each clause has exactly three literals. We're going to prove that the problem 3SAT is NP-complete. The easy part, as is often the case, is that 3SAT is an NP. We already saw that the general problem SAT is an NP. Just guess a truth assignment and check that it makes the expression true. Since 3SAT is a special case of SAT, the same non-deterministic algorithm works for 3SAT. We're going to prove the NP completeness of 3SAT by polytime reducing CSAT to 3SAT. We might suppose that the way to do that was to find a polynomial time algorithm to convert every CNF expression into a logically equivalent 3CNF expression. But not only can you not do that in polynomial time, you can't do it at all. That is, there are Boolean expressions that simply have no 3CNF expression. I'm not going to prove that formally, but an example is the expression with 4 variables that is true if and only if an odd number of the variables are true. That is, exactly 1 or exactly 3 of the 4 variables are true. Fortunately, the reduction does not have to preserve equivalence of the input and output expressions. Since we are dealing only with whether expressions are satisfiable, all we need to preserve as we transform the input expression to the output expression is that either both are satisfiable or neither is. Thus, we're going to give a polytime reduction that does not preserve equivalence. In fact, it doesn't even preserve the set of propositional variables. Rather, it introduces new variables into clauses that have more than 3 literals in order to split them up into many clauses of 3 literals each. So, consider a clause with k literals, x1 through xk. Remember, these are literals, not variables, so any of the xi's could be not followed by a propositional variables. We need k minus 3 new variables, which we'll call y1 through yk minus 3. These y's appear in no other clause, and they're really variables, not literals. Also notice that if k is equal to or less than 3, then no new variables are introduced. We're going to replace the clause x1 through xk by k minus 2 clauses. The first consists of the first 2 literals, x1 and x2, and the first new variable unnegated, that's y1. The second, which is this, has only one of the original literals, x3, and 2 variables. The previous variable, y1, is negated, while the next variable, y2, is not negated. That pattern repeats. Each new clause has one of the original literals, say that, a negated previous y, and an unnegated next y. Then finally, the last of the new clauses has the last 2 of the original literals and only the previous y negated. We need to show that when we make this change, the new expression is satisfiable if and only if the original expression was. For the first direction, we'll show that if there is a satisfying truth assignment for the original expression, then we can extend this truth assignment to also provide truth values for the y's that will make the AND of all new clauses true. So suppose that there is a satisfying truth assignment for the original expression. Then this assignment makes at least one of the literals, the x's, true. Say it makes xi true. Then we can assign y sub j the truth value true for j less than I minus 1, and assign y sub j the value false for y equal to or greater than I minus 1. For this truth assignment, the clause with xi, that is this one, is made true by xi. all the previous clauses, those there, can be made true by their unnegated y's, and all the later clauses, all of these, are made true by their negated y's. Conversely, suppose that there is a truth assignment that makes all the new clauses true but makes none of the literal x's true. Assuming that no x's are true, the fact that the first clause is true, that is this, says that y sub 1 must be true in this hypothetical truth assignment. And then the second clause says that since x sub 3 is false and not y sub 1 is already known to be false because we had to make y1 true, that means that y2 must be true. We can reason the same way to show that all the y's are true. But then the last clause, this, which has only false x's and a negated y, must be false. We have shown that when we convert one long clause of the input to a sequence of clauses with 3 literals per clause, the satisfiability or non-satisfiability of the expression is preserved. We can repeat this argument for every long clause, thus converting the original expression to an expression with at most 3 literals per clause, and that is satisfiable if and only if the original is. Technically, we are not done because the original expression could also have clauses that are too short. For a clause with only one literal x, we introduce 2 new variables, y1 and y2, and replace one clause by the 4 clauses shown. Notice that the y's appear in all 4 combinations, so if x is false, one of these 4 clauses will be false, no matter what truth values we assign to the 2 y's. For example, if y1 is true and y2 is false, then this clause will be false whenever x is false. But conversely, if x is true, then all 4 clauses are true regardless of the truth values of y. And don't forget that these introduced y's are new. They appear in no other clauses, just like the y's we introduced to split apart the long clauses. And the final case is a clause with 2 literals, say w and x. For this clause, we introduce one new variable y and replace w plus x by 2 clauses, one with a non-negated y, the other with a negated y. The same argument as for the clause of a single literal applies here. If a truth assignment makes both w and x false, then one of the 2 new clauses will be false. But if the truth assignment makes at least one of w and x true, then both new clauses can be made true. The conversion of the clauses from the input CNF expression to clauses in 3CNF takes only linear time in the length of the input sequence. That is, we run through each long clause generating new variables and new 3 literal clauses as we go, taking time that is proportional to the length of the original clause. The constant of proportionality may be large, but the algorithm is still linear. Well, we have to be careful, as always, to remember that there is a finite alphabet involved. That means when we create new variables, the y's, it may take log n time to write down their numbers, so the algorithm really could take order n log n time to generate the output expression. But as always, we'll ignore factors of log n. They cannot take us out of the polynomial class. We thus have a polytime reduction from the problem CSAT to the problem 3SAT. And since CSAT was shown NP-complete by the modified construction in Cook's theorem that produced the CNF expression, it follows that 3SAT is also NP-complete.